I want to use this circuit to show you how to use Kirchhoff's voltage law. This is a combination series and parallel circuit. We have three resistors. You know the different resistance values. We don't know the value of the power supply, but we do know the current through resistor 3. So the first thing that we're going to do here is just label our different voltages. So power supply is the total voltage. I'm going to call this V1. I'm going to call this V2. I'm going to call this V3 because it corresponds with the table that we have. So it's important to be able to do that. Now the next thing I'm going to do is I'm going to create a loop. And I'm just going to create a loop right here, just on the left-hand side, just using the power supply resistor 1, resistor 2. So if I do that, I'm just going to define the direction as clockwise, which means that VT is gaining potential. So we have a positive value for the total voltage. V1, it's in the direction of the current, so it's going to lose some potential. So potential is going to go down, so minus V1. V2 is also in the direction of the current, so the current's going to flow this way, and so we're going to lose potential as well. If you think about it, potential should be 0 down here. So we're going to have some positive potential down to some 0 potential, so we're going to lose potential, so that's minus V2, and that equals 0. So if I just create another loop here, which is important, I can create this loop over here just on the right-hand side. So just these two resistors, R2 and R3. I'll define that clockwise as well. And if this is clockwise, V2 going in the direction that we're defining it, from this node to this node is gaining potential. So V2 is positive. V3 is going to be negative. It's going to be losing potential. So it's going to go down. So minus V3, that equals 0. So these are two different loops that we have. Now, I could have created a different loop here where I could have created just the outside using R1 and R3 and not worrying about R2. You'd end up getting the same result, so you really don't have to worry too much about that. Now, the other thing I wanted to kind of point out here is that when we're using Kirchhoff's voltage law, very rarely are we going to use Kirchhoff's voltage law alone and only Kirchhoff's voltage law. Usually we're going to have to use a combination of Kirchhoff's voltage law and Kirchhoff's current law. So you'll see that here as well. And when you're working on some different problems, don't be surprised if you have to use a combination of the two of them in order to solve some of the different problems. But before we get to that, I'm just going to substitute in what V1, V2, V3 are in terms of Ohm's law. Because I know V1 is equal to I1 times R1. I know V2 is R2 times I2, and I know V3 is I3 times R3. So I can substitute these values in and see where we go. VT, I'm just going to leave that alone because I know that's just going to be the power supply. So I'm just going to leave it as it is. Now you notice I put equal here because I'm just going to add V1 and V2 to both sides. And if I do that, I have I1 times R1 plus I2 times R2. Same thing over here. I'm going to add V3 to both sides. So if I do that, I have I2 R2 equals I3 times R3. Now what I can do is substitute in some of the values. So if I do that, don't know I1, R1 is 570 ohms. Don't know I2, R2 is 390 ohms. Then over here for our other equation, I have I2 times 390 ohms equals, now I3 is 5 milliamps. 5 milliamps is 0.005 amps, and you have to make sure you leave that in amps. So 0.005 amps times R3, which is 250 ohms. So what I can do here is I can solve this right equation for I sub 2. So if I do that, let me just use my calculator. I just multiply 5 milliamps, so 0.005 amps, times 250 ohms. I take that and I divide it by 390 ohms, and I get a result here. I'm going to round this to 4 decimal places, even though hopefully by this point you've seen that you shouldn't be rounding too much. 0.0032 amps. So that's going to be the current I2. Now what I can do is I can actually substitute this back in here. So if I substitute I2 back in, just going to use another color again. So VT equals I1 times 570 ohms plus I2, which is 0.0032 amps times 390 ohms. And that's what I get. But unfortunately, I still have two variables. This is where I have to use Kirchhoff's current law. So using Kirchhoff's current law, I know that this is my current I1. I know that this is my current I2. This is my current I3. I know that I1 equals I2 plus I3. Since I already know I2 and I know what I3 is, I can figure out I1. So I1 is equal to 0.0032 amps plus 0.005 amps. So that's going to give me 0.0082 amps. So that's going to be I1. Now what I can do is I can substitute that right back into the top equation I have, or the equation I have in purple, and I can figure out my total voltage. So I can use that to figure out the power supply that I have in this circuit. So if I do that, total voltage is equal to 0.0082 amps times 570 ohms plus 0.0032 amps times 390 ohms. So if I just figure that out, so 0.0082 times 570 plus 0.0032 times 390, that gives me a total voltage of 5.922 volts. So now if you take a look at what we can do here, I can plug in 5.922 volts for the total voltage. I also know the individual currents, so I know that I1 is 0.0082 amps. I know that I2 is 0.0032 amps. The total voltage is the same as, the total current is the same as the current through I1. So the total current is also 0.0082 amps. So current coming out of the power supply is equal to the current going through V1. So now all I have to do is use Ohm's law and I can figure out the rest. So if I do that, so 5.922 divided by 0.0082 gives me a total resistance of 722.1951 ohms. 570 times 0.00570 times 0.0082 is 4.674 volts. 390 times 0.0032 is 1.248 volts. And then 250 times 0.005 is 1.25 volts. You notice that these two, they should be the same, but they're a little off because of the rounding. But that's it. So that's how you could use KVL, a little bit of KCL in here in order to solve this problem.